Good afternoon and welcome to the webinar. If any of you attended the first webinar I did a few months ago on crystals and frequency products, you may recognize the first few slides. After these, however, we're going to be looking at issues that occur when a smaller packaged crystal is designed into the circuit. Anyway, this is the agenda for today's webinar. I'm not going to go through each one now, as we'll come to that in a minute. IQD have been manufacturing and selling frequency control products for 47 years. The company was founded in England in 1973 and the head office is still in the same town in the county of Somerset. IQD are one of the leading brands of frequency control products, especially in Europe, and have active customers both direct and through distribution in over 50 countries. The company opened the US operation in 2012 in San Jose and has since relocated to Palm Springs in Southern California. Back in 2017, the company was acquired by Worth Electronic, and IQD are now a standalone profit and loss company within the Worth Electronic group of companies. IQD's range of products includes quartz crystals, clock oscillators, voltage controlled crystal oscillators, known as VCXOs, temperature compensated crystal oscillators, TCXOs, oven controlled crystal oscillators, OCXOs, and disciplined OCXOs and rubidium oscillators. Today's presentation is focusing on quartz crystals and clock oscillators. So what are frequency products? Well, they are electronic components that basically provide the timing in all electronic circuits. They are in fact the heartbeat of the electronic circuit, and although the microprocessor, semiconductor, is the brains, just like a human, without the heartbeat, they do not operate correctly. Worth Electronic are now promoting a range of quartz crystals and clock oscillators, which are key products within the frequency control market. So let's go right back to basics and look at how quartz is grown. Many years ago, raw quartz was used to manufacture quartz crystals. However, the yield, due to poor quality and the cost of mining, etc., meant that quartz crystals are now manufactured from synthetic quartz. It all starts from a seed of silicon dioxide, SiO2. Silicon dioxide actually makes up 10% of the Earth's crust and is also known as silica. Anyway, quartz crystals used in electronic components start their life as a seed of silicon dioxide. The synthetic quartz bar is physically grown in an autoclave. This is a large oven which can be as tall as 3-story building and will have 18-inch thick walls. The seeds are put onto hooks at the top of the oven, and the raw quartz, or clinker lasca, is at the bottom of the oven. This is then heated to temperatures as high as 400 degrees centigrade, that's 750 degrees Fahrenheit, and at a pressure of 1,360 atm. After about 1 to 3 months, depending on the size of the bars required, the synthetic bars are ready to be processed. And in this picture here on the right, you can see them. They're like stalactites hanging onto the hooks that the seed was put on originally. And each of those bars are going to be around about 8 to 9 inches in length. The synthetic quartz bars need to be cut into wafers. A diamond cutter is used, and this takes many hours depending on the thickness of the quartz bar. It is really important that the angle of the cut is accurate, and for most megahertz quartz crystals, the standard cut is in fact AT cut, highlighted in the picture in yellow. This means that the angular cut needs to be 35 degrees and 15 seconds. Anything different will mean that the quartz will not operate correctly. The quartz these days are cut into rectangular blanks, as the vast majority of the surface mount packaged crystals will use this type. The large circular blanks are used in the older HC49 package types. So what do we do with the blanks now? Well, the frequency is determined by the thickness of the quartz blank. The higher the frequency, the thinner the quartz, and of course the lower the frequency, the thicker. So the blank has to be lapped or in layman terms, ground down to the correct thickness. This is done on a machine which uses fine grit to wear away the quartz that is not required. So we have the quartz blank at the correct thickness, but we need to find a way of attaching the electrodes. We screen off the area that we don't want to add the metal to, and it leaves an area which we add gold or more typically silver. This in fact adds the thickness to the quartz blank. So when we lap the quartz to the correct thickness, we have to allow the electrodes and silver as well. The blank is then mounted into a package. This photo shows the old HE49 package as it's easier to see because it's such a much larger blank. Assembly then goes through final adjustment to assure that the frequency is correct and operates within the required stability across the whole temperature range specified by the customer. Finally, the package is hermetically sealed as the cavity inside the package needs to be a vacuum as the quartz needs to oscillate. A 10 megahertz crystal oscillates 10 million times a second and a 50 megahertz crystal 50 million times a second. We now have a completed quartz crystal, and as you can see there, a fully packaged old style HE49U. So why are quartz-based products required, and why don't customers just use the internal resistor capacitor, inductor capacitor in the microprocessor? Well, the quartz-based products are much more accurate than the RC-LC circuits. These operate at 20,000 parts per million at 25 degrees, whereas a quartz crystal can have a stability down to 10 parts per million, and standard clock oscillators have a stability as tight as 20 parts per million, and in some cases even lower. BCXOs have a stability down to 25 parts per million, and then when we get to TCXOs, the stability is as tight as 50 parts per billion. And then going to the next level, OCXOs, that's even tighter, down to 0.2 parts per billion. And finally, the rubidium oscillator, which are 100 times more accurate than even an OCXO, has a stability of 0.05 parts per billion. As you can imagine, it's more difficult to manufacture a rubidium than a 10 ppm crystal. And of course, the price difference between the different product types reflect this. One of the problems using quartz is that frequency is affected by the change in temperature. All quartz crystals are tested at 25 degrees C and have an initial tolerance measured in ppm at 25 degrees C. The diagram shows the different angle cuts of the crystal, which affects the stability over the operating temperature range. You can see that the yellow line within the red triangle, going through the middle there, shows 20 parts per million stability over minus 40 to plus 85. And the angular cut is 35 degrees, 15 seconds, with a tolerance of plus 2 seconds to plus 6 seconds. Some stabilities are just not possible over certain operating temperature ranges. For example, plus or minus 10 ppm stability over minus 40 to plus 85 degrees C is not possible. This is shown on the diagram as the brown line, and you will see it lead the red box at minus 10. There's that there, and at plus 60. Some of our competitors say that they can manufacture this spec. With very poor yields, they may be able to, for sample quantities, but not in high volume, and be able to achieve good yields. So a quartz crystal on its own will not operate, so an oscillation circuit needs to be used to make the crystal work. The most common is the Pierce oscillation circuit, which comprises of two capacitors. We'll come back to these later when talking about low capacitance. It also comprises of a resistor and also an amplifier and a further resistor. The resistor RF and the inverter are normally situated within the microprocessor. I mentioned low capacitance in the previous slide, and I just want to spend a short time looking at this. Low capacitance is the capacitance of the oscillation circuit when presented to the quartz crystal. This is normally measured in picofarads and is very important when using a quartz crystal that it has the correct load capacitance. Depending on the size of the quartz crystal, the frequency can be off center as much as 20 part per million just by having load capacitance incorrect by 1 picofarad. So how is the load capacitance calculated? It is a complicated equation which takes the values of the capacitors in the Pierce oscillation circuit and first multiplies the values, in this case of CA and CB, and then divides the total against CA added to CB. So for example, if CA is 30 picofarad and CB is 30 picofarad, then the total will be 30 times 30, which is 900, divided by 30 plus 30, which is 60, which gives us 15 picofarad. However, we then have to add the stray capacitance. This includes the PCB stray capacitance and the IC input capacitance, and this is typically between 2 and 5 picofarad. So in this example, you would need to guess what stray you use in the calculation, say 3 picofarad, which means the crystal load capacitance would need to be 18 picofarad. By changing the CA and CB values and maybe also using the crystal with a different capacitance load, the engineer can change the circuit and ensure that the quartz crystal operates correctly. As mentioned just now, the incorrect load capacitance will pull the frequency off center depending on the size of the quartz. This diagram shows the HC49 metal can package, which uses a large circular blank, and the CFPX 180, which is a 3.2 by 2.5 millimeter package, which uses a small rectangular blank. The larger HC49, which is the black line, is pulled off frequency a lot more, and you can see that with a 5 picofarad difference, the stability is as much as 50 part per million off center frequency, whereas the CFPX 180, the red line, is only approximately 5 part per million off center. Shunt capacitance, C0, is another part of the crystal specification that we are all often asked about. The frequency can change by a few part per million depending on the ratio of the C1 to C0 and CL. The ratio determines the sensitivity of the actual frequency to changes in the external circuit. The smaller the crystal blank, the smaller the C0 value. Shunt capacitance is really only an important parameter if you are in fact designing a full crystal oscillation circuit. In most cases, the oscillator circuit, which we saw earlier, the amplifier and the resistor is within the semiconductor, and C0 is not a concern. The drive level of the crystal is another parameter that we need to review. The quartz crystal is designed to actually vibrate under the electrodes. In this photo, that would mean under the keyhole-shaped plating on the quartz crystal. The clear part of the quartz is there to dissipate the vibration before it reaches the edge of the quartz blank. Probably a good time to remind you that, for example, a 25 megahertz crystal is vibrating 25 million times a second. If the vibration reaches the edge, we have a ripple effect. Think of a pond of water. You drop a stone into the water and the ripples spread out, but you want to stop the ripples before they reach the edge of the pond, which is not easy. In a crystal, these reflection waves will cause harmonic and ESR changes. Think about two boats passing closely together at high speed. The waves caused by the boats meet and the waves get larger, then turn back on themselves and the boats are rocked violently. If this happens with a crystal, the crystal will not operate and the mounting structure will start to break. It could also cause frequency and ESR change. Remember, the higher the drive level, the higher the risk of damaging the crystal. And it's very difficult for us on a little bit of quartz like that, or even smaller these days, if you think of a 2.5 by 2 millimeter package, to actually keep the vibrations under the plating and not to reach the edge of the quartz. I want to spend a little time looking at the issues you may come across when redesigning circuits using smaller crystals. Electronic components are getting smaller and smaller, and many of Worth Electronics crystals are really small, down to 1.6 by 1.2 millimeters. The original oscillation circuit used larger crystals, HC49, 4HSMX and 7 by 5, for example. So what happens when you use a smaller crystal? The first thing we need to discuss is equivalent series resistance, which is known as ESR. This is how much energy is lost in the quartz crystal, and the level of ESR required is normally specified by the chipset manufacturer and as a small range or even just a figure shown in the reference design or on application notes. ESR is measured in ohms, and actual ESR will change depending on the actual frequency, the package type, the size of crystal, and the size of electrode and mounting structure. For this discussion, we are focused on the size of the crystal. Our data sheets show the ESR, and we will always show a higher figure. This allows a good yield in manufacturing, and when we measure the ESR, the actual figure will be a lot lower. So our data sheets actually show the worst case. If, for example, the ESR of the crystal was 70 ohms, and we specified our data sheets as 70 ohms, then the yield we would have very poor yield if in fact the majority of them were 75 or 80. So that's why we would actually put that as 100. If there is too much ESR, the crystal will not start oscillating. And this has become a much bigger issue over the last few years as the package sizes have got smaller. The smaller the package, the higher the ESR. And we see a lot of issues as chipset companies use larger package crystals on their reference designs. I fully understand why someone wants to use a larger package. They can hand solder rather than a smaller 2.5 by 2 millimeter part you can hardly see. However, this leads to issues when the reference designs calls for a metal can surface mount package and an ESR level of 40 ohms, and where the customer application requires a smaller crystal, say 2 by 1.6 millimeter, which has an ESR of 200 ohms. Now the customer has a major issue and the crystal may not start. Just be aware of this issue, and if needed, contact us and our engineering support team will be able to help you. I mentioned that too much ESR and the crystal will not operate due to negative resistance ratio. For the crystal to oscillate, the gain of the amplifier, which is normally within the chipset, must be larger than the impedance of the loop. Negative resistance ratio is the negative resistance, which is the amplifier gain divided by the ESR. So for example, if the ESR of the crystal is 60 ohms, then to obtain oscillation, the negative resistance must be higher than 60 ohms. For OK oscillation, the negative resistance would need to be 3 times 60 ohms, which is 180. A good stable oscillation, the negative resistance would need to be over 300 ohms. The issue is that the smaller the crystal, the higher the ESR, which means that the negative resistance is not as high and would cause a ratio of 1 or lower. A typical ESR for a 25 megahertz 1.6 by 1.2 millimeter crystal is in fact 200 ohms, which means the negative resistance should really be 1000 ohms for good stable oscillation. And this is really important because if this isn't correct, then the crystal won't start and it won't oscillate, and then we need to look at redesigning. A way to improve the negative resistance is to look at reducing the capacitance load of the crystal. The lower the load capacitance, the higher the reactance, XC. And this in turn means that at CA and CB, there is less current being routed to the ground. Therefore, lower capacitance load leads to lower current draw, which also means less amplification is needed to achieve the same voltage out. The key is the lower the low capacitance, the higher the negative resistance. As we saw in the last slide, with the smaller crystal having higher ESR, we need a higher negative resistance to give us stable oscillation. In conclusion, regarding designing in smaller size crystals, the frequency of the crystal will change if the incorrect low capacitance is used in the circuit. The bigger the package, the bigger the frequency change. The smaller the crystal, the higher the ESR. This leads to a smaller negative resistance ratio and issues with the crystals actually starting to oscillate. To improve the negative resistance, you can lower the low capacitance. So, although it sounds quite complicated, I really hope that the last few slides have helped with any issues you may have designing in smaller crystals, or give you an idea of some of the issues you may face when you come to do this in the future. Of course, if you have any issues, just contact our engineering team through us, through your ADM, and we'll be able to help you get through these issues. As I mentioned earlier, Worth Electronic are now promoting and selling frequency control products, and they've been doing this for about a year. There are 3 product types currently in the Worth catalogue. The first product type is the 32.768 kilohertz watch crystals, which are available in both surface mount and through-hole packages. In total, 9 different models and 25 different part numbers are stocked. By the end of Q3 this year, a smaller 1.2 by 1 millimeter package will be added, which will have 4 different capacitance loads: 4, 6, 7, and 12 picofarad. The second product type is the quartz crystals, surface mount quartz crystals, and a range are available from 3.276 megahertz to 50 megahertz. And these are surface mount, and there are a few through-hole packages as well. 9 different models and 283 part numbers are in stock. By the end of Q3, a 1.2 by 1 millimeter crystal will be added, and there'll be 11 new part numbers, 11 new frequencies and specifications. And finally, surface mount clock oscillators with a frequency range from 3.6864 megahertz to 125 megahertz, 8 models and 208 part numbers. By the end of Q3, another 16 new models and 79 new part numbers will be added. And all of these part numbers will be stocked at Worth Electronics. So the quartz crystals will start, part number will start with 830, and the clock oscillators start with 831. So the products can be found on the Worth Electronic website, and here is a snap of what that looks like when you get to that part of the website, which is the frequency products. You have a section for quartz crystals, a section for watch crystals, section for clock oscillators, and then there's the design kits as well, which we'll come to later. And on the left there's a parametric search. So if you know what you're looking for or a range, you can put that in and it will bring up those parts that meet your criteria. Once you go down to into the site itself, this one is for the quartz crystals. You have the models, the IQXE26, etc., and the size. And then along the bottom, the tabs, and as you click on each one, what's available will come up below that. And as you can see under the downloads, you've got the Eagle and the CAD tools as well, which are available. And if the parts are in a design kit, on the right-hand side, you'll see the number like 83003, which is the design kit for these crystals, and those parts are in the design kit. The design kits actually help engineers have components readily available, and Worth Electronic have introduced 3 different design kits for frequency control products. There's one for the 32.768 kilohertz watch crystals, one with surface mount ceramics, packaged quartz crystals, and the third is the metal can through hole and surface mount crystal. We are still working on doing a design kit for the clock oscillators, but that's been a bit more tricky as we need to screen that box. If you'd like one of these, then please contact your Worth Electronic ADM or IDM. So what does the typical quartz crystal specification consist of? Well, frequency, of course, which is normally in megahertz. Unless it's a watch crystal, then it'll be in kilohertz. The physical size of the package, normally in millimeters. The initial tolerance, which is always measured in parts per million. The stability over the operating temperature range, which again is in parts per million. And of course, then we need the operating temperature range, which is normally from a negative to a positive Celsius temperature, for example, -40 to +85 degrees C. Then we need the low capacitance, which we know is in picofarad. And finally, if needed, we need to know what ESR is required for the crystal, which, as we heard earlier, is in ohms. I have mentioned the words watch crystal and the frequency 32.768 kilohertz in previous slides. Many electronic circuits use real-time clocks, which enables the clock to operate when power is switched off or for date and timestamp activities, which are getting more and more common in many of the current electronic products. In all cases, a real-time clock requires a precise frequency to keep time, and that frequency is 32.768 kilohertz. The reason 32.768 kilohertz is used is because if you divide it by 15 times, you reach 1 hertz, which relates to 1 pulse per second. The watch crystal specification is slightly different from the megahertz crystal. Of course, the package size is required, and then there is a tolerance, normally plus or minus 20 parts per million, and a low capacitance also. The difference is the stability across the operating temperature range is not required. The diagram shows a parabolic curve with 0 parts per million at 25 degrees C, which is the top of the curve. As the temperature changes, the stability also changes. So at -50, the stability could be down to -200 parts per million, and at +75, the stability could be at -100 parts per million. So we show a temperature coefficient on the data sheet, for example, -0.035 part per million per degree C squared. So these are the quartz crystal packages that are currently in the Worth Electronic catalogue and in stock. As you can see, the largest is the HE49 through-hole package, which is up on the top left. And the package sizes go right down to the IQXE26, which is a 1.6 by 1.2 millimeter package. Just remember though, that the smaller the package, the frequency range will start up at a higher megahertz. For example, IQXE26 starts at 24 megahertz. As you can see, we also add the IQXE240 because that part's been added Q3 2020. And these are the watch crystal packages currently held in stock. The sweet spots for pricing and package sizes are the CFPX217, which is the 3.2 by 1.5, and also the IQXE25, which is the 2 by 1.2. The large black plastic packages are going obsolete. Basically, they're just the old cylindrical part inside of a molding, and economically and environmentally, they're not good for us. And you'll see on the right, we've got another 1.2 by 1 millimeter package coming in, but it's the wrong picture. It's not an IQXE240. It'll have a new model number. I've mentioned clock oscillators in the presentation and just want to look at this type of frequency control product. As you saw earlier, a quartz crystal requires an oscillation circuit to make the crystal oscillate. Well, a clock oscillator is basically the quartz crystal and the oscillation circuit within one package, a plug-and-play crystal. It doesn't allow the design engineer to tweak the circuit, but it is easier to design in. A typical clock oscillator specification consists of frequency, megahertz, the package size, and with a clock oscillator, the output type is specified. This can be HCMOS, low voltage positive emitter coupled logic. Thankfully, we shorten that to LV-PECL. Low voltage differential signaling, shortened to LVDS, or clip sine wave. Currently, Worth Electronic are only stocking HCMOS, but LV Peckle and LVDS will be added by the end of Q3. Unlike a quartz crystal, we only specify the stability and not the tolerance. The stability in parts per million also includes the tolerance, aging, change due to supply voltage, and the output load. Again, we have the operating temperature range in degrees C and supply voltage. Worth Electronic currently stock 5 volts, 3.3, 2.5 and 1.8 volt, but will also be stocking 1.2 and 0.9 volt by the end of Q3. These new lower voltages are very popular in the latest designs. And finally, some of the clock oscillators have a standby or enable disable tri-state function on pin 1. These are the clock oscillator packages currently stocked. They are industry standard size packages from 7 by 5 down to 2 by 1.6 millimeter, and in Q3 we'll be putting a 1.6 by 1.2 millimeter package into the portfolio. In Q3 2020, we will be adding a range of 32.768 kilohertz clock oscillators, not crystals, but clock oscillators, into the Worth Electronic catalogue. The package sizes will be from 3.2 by 2.5 millimeter down to 1.6 by 1.2 millimeters, and these will be very low power products, very accurate 20 part per million tolerances. At the last webinar, I was asked about testing processes. All our products are tested at the UK facility before being shipped to our customers. We test products using the AQL system based on BS EN 6001 MIL-105, and the table shows the lot acceptance plans that we test to. This is a good place to remind you that our returns from the field due to technical issues last year was 0.0033%, which equates to 33 parts per million. Now, obviously, we would like that to be zero defects, but we're trying to improve on this, but we know that some of our competitors are quite happy at 10%. Finally, I want to run through a few applications where the quartz crystals and clock oscillators that are stocked can be used in. The first is audio-visual broadcast. As you can see, the frequency stocked can be used in digital audio, TV, DVD, and set-top box applications. These include body cameras worn by police and security agencies, CCTV cameras, and license plate recognition systems. Another application is wired communications, including fiber optical transmission systems. Again, you can see the frequencies can be used in Ethernet, Gigabit Ethernet, fiber channel, SONET, SDH, and USB applications. Also, in wireless communications, which is an area of the electronics market that is rapidly growing, will grow even faster once full 5G is developed and in the market. The frequency products stocked by Worth Electronics can be used, for example, in Bluetooth, near-field communication, remote tracking location systems, and Wi-Fi applications. Industrial applications are one of the largest markets that our products are used in. They can, for example, be used in access control, battery charging, smart meters, home security, and solar panel inverter applications. I hope that this has helped you understand frequency products, especially quartz crystals and clock oscillators, a little more. Your local Worth Electronic ADM is there to assist you, and if you require frequency products not currently stocked by Worth, then the ADM will contact us here at IQD and we'll be able to assist you. I'm now open for any questions from the presentation or any questions people have on crystals, oscillators, frequency control products. So one of the questions we got is, do you sell oscillators with user programmable frequencies? Our oscillators, we do sell a range of programmable oscillators, but they're programmed at IQD and not by the customer. And these come out to you already with the fixed frequency. Another question, do crystal oscillators have starting problems at very low temperatures, such as below -40 or -55 degrees? Very good question, and that goes back to what I said earlier. If there is issues with the circuit, with the amplification issues there, they're more likely to be at the lower temperature than the starting temperature, the higher temperature, sorry. So where we have seen issues is if a product is at -40 degrees for a very long time and there is the negative ratio issue, then it's more likely to happen at the colder temperatures rather than the warmer temperatures. But we would test our products across the whole temperature range, so we would know our products would operate, but it just depending on the circuit the engineers designed and whether or not the negative resistance ratio is correct or not. Right, question, what kind of validation test should be done by end user to validate proper operation of a crystal in a circuit? That's a very good question. And one I will get our engineering team to write in more detail. What I would say is that when you come to actually, for example, if you already designed a circuit and you've put the crystal in there, one of the competitors, and you're looking to change it for somebody else, whether it's IQD, Worth, or anybody else, then the electrical specification that you have in front of you could be identical. The two would look identical. But when you put it into the circuit, your circuit, one of them might not work properly. The new one might not work properly. So that is why we always ask for the full specification, everything else that's going on with the circuit, to make sure that the products we supply match what you need in your circuit. But I will come back to Worth and they will be able to let you know what the validation tests are for a new crystal in a circuit. Have we any more questions? Obviously, if you have any questions, you can email them to Worth Electronics or to your ADM, and we'll be able to reply with full details on email, and if needed with diagrams and documentation. Okay, if there's no more questions, I'd like to thank everybody for joining the webinar, and hopefully for you having an easier life when designing in crystals and oscillators. Thanks very much.